Hello students, today we will do chemical bonding and molecular structure theory. So what are the topics that we are going to cover today? So Coase-Lewis approach first we will see, which is the first approach. Ionic or electrocovalent bond, lattice enthalpy and its calculation, covalent bond, calculation of percentage ionic character, dipole moment, partial ionic character of covalent bond, Fajan's rule, bond parameters, resonance, coordinate bonding, valence orbital bond theory, concept of hybridization involving sp and d orbital, VSEPR theory, molecular orbital theory, which was given by Hund and Mulliken, hydrogen bonding, effect of hydrogen bonding, and metallic bonding. Then we will sum up with a summary. Okay, so let us start our today's class. So, disclaimer: the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of these images used in the slide deck and have any concerns or issues, please contact us at sathee@itk.ac.in and we shall remove the images. So first was the Coase-Lewis approach. So it was based on the octet rule. So it says that the electrons in the outermost shell will be 8. So this is a very basic rule, we have seen it often. And in some elements it can be 2 also, like in the case of hydrogen, lithium and beryllium. So Coase-Lewis says that during the formation of the compound, the atoms are take parts in the reaction, chemical combination such that its octet can be completed. Now in the Lewis symbol, the number of dots represent the electrons. So how do we draw it? We take the element symbol, which is suppose for hydrogen it is H or for sodium it is Na. We take those symbols and put dots around it to represent the electron. Cross can also be used to create a sense of differentiation. Okay. Now it can also be used. The number of electron is used to calculate the valency. We know it very well. For suppose we are taking sodium, if you know the valence electron, if it is 1, its valency is +1. So as simple as that, and accordingly we do the same thing so that its octet can be completed. So what are the limitations of octet rule? First of all, it doesn't tell about the shape of the molecule. Okay, means the orientation and the shape is not at all discussed here, and the relative stability is also not discussed here. So they are just attaining the 8 electron, and what is the resulting stability, that is not being discussed. In addition to that, we have a difference of octet rule also, means in the number of valence electron also. The first case is electron deficient compound, which are also called as hypovalent compound. So in this case, your BCl2, if you draw the Lewis dot structure, there will be 4 electrons. For boron, for Bf3 6, AlCl3 also 6. Whereas there is hypervalent compound or electron rich compound. So in this case, you will find that since 5 chlorines are there, each giving 1 electron, that will result in total 10 electrons. SF6 12, IF7 14. Now you can see that it is always greater than 1 in case of these things, whereas in this case it is less than 1, less than 8. Now the third is the most, you can say the most unappropriate exploitation, means violation of the noble say octet rule, which is the noble gases taking part in the formation of compounds. So you can see that they have a noble configuration. They are having 8 electron in the valence shell. Still, they are eager to form the electron. Means although this requires a very high external agents like temperature and pressure, but they do form it. So you can see that 10 electrons are there in X2, and here it is 14 for Xe and 8 for 12 in this xenon, and in this KrF2 the krypton is having 8 plus 2 10 electrons in total. Okay, and at last we have this anomaly of this odd electron. So these compounds, you will see that they have an odd number of electrons, and for example H2 plus, if you take, there is 1 electron, and this 1 electron is being distributed between 2 atoms. Okay, so these are the some examples. Then we have NO2, Cl2. So they form bonds, and those bonds are including only odd number of electrons. So this is also a exception of this octet rule. Next is ionic or electrovalent bond. So ionic or electrovalent bond are formed when, so it is formed when elements of high electronegative difference. So if one element is highly electropositive, other is highly electronegative, then they form this kind of bond, which is ionic bond, in which there is complete transfer of electron. Okay, so how it is formed? Let us take an example. So it is formed by the complete transfer of electron from one atom to another. I have said this. So for example, we have taken Na and Cl as the most common example, where Na is having 11 electrons and chlorine is having 17 electrons. Now, if one electron is transferred from sodium to chlorine, then sodium will have 8 electrons in total in the valence shell. Okay, and if one electron is being added to the chlorine, then it will also result in 7 plus 1 8 electrons. So both have a complete valency. So in this way, the electron is transferred from sodium to chlorine, forming sodium chloride. So this is your salt. Now, most important thing about ionic bond is that they are non-directional in nature. Means the ion this is coming from any direction. It is not defined. Okay. And second thing is that they are highly polar, because this is having a complete positive charge and a complete negative charge, and they are separated by a distance. Therefore, it is highly polar in nature. Next, what are the effects that are affecting the formation of ionic bond? The first following factors are, the first factor is low ionization energy of the electropositive element. So if the electropositive element is having a low ionization energy, then it can easily lose its electron at a lower energy input. So it can form the ionic bond easily by transferring electron. Second is high electron affinity of electronegative element. So if the electronegative element has a high affinity towards the acceptance of electron, it can easily accept the electron and hence can completely octet to form the ionic bond. And the next is high lattice enthalpy. So lattice enthalpy is basically the energy released when the moles of gaseous atom combine to give the complete lattice. And if that energy release is sufficiently high, that means the compound that is formed is highly stable, as it is in the lower energy state. So we can say that the lattice enthalpy is directly proportional to charge on anions and size of ions. So if the charge is more, they will come closer and closer, and greater force of attraction will be there. And if the size is large, then that would result in an inverse relationship between the lattice enthalpy, because the electrostatic force is inversely proportional to the size. So what we are doing inversely proportional to the distance. So size will increase, the distance will also increase. So this is a direct effect of the electrostatic force. Okay. So if you take the element of group 1 and group 2, they combine with halogen, oxygen and sulfur to form the ionic compound. Now bonding in compound of transition metal in ionic have partial covalent character. So this is very important. You will see that group 1 element like sodium or cesium or your potassium, they all can lose easily. They all can easily lose electron and form the ionic bond. Whereas the case in alkali metal also, like magnesium also and calcium, they all can lose 2 electron and form the ionic bond. Whereas in case of transition metal like our iron and zinc and all, they are having, okay, they are ionic in nature, but the covalent amount is also there in the bond. Clear? Now lattice enthalpy and its calculation. So this is done with the help of Born-Haber cycle. So what is lattice energy? It is the energy that is required to separate 1 mole of a solid ionic compound into its gaseous constituent ions, right? So if you take 1 mole of a lattice, okay, 1 mole of the lattice, suppose you are taking 1 mole of NaCl, clear, and you are separating Na and Cl, and those are going to the gaseous state, then you are saying that, okay, our energy that is being required is called as lattice enthalpy. So what does Born-Haber cycle includes? So it includes, first of all, vaporization of reactant into gaseous state. If it is not in gaseous state, then conversion of this gaseous atom into ions by the removal of electron, okay, or by the addition of electron, means cation or anion formation, both. Then we have the combination of these two, means your positively charged gaseous atom and negatively charged gaseous atom to form the lattice. For example, this M solid is reacting with X2, half X2 to give Mx. This delta H here is the enthalpy of formation or the enthalpy change of reaction. Then Q is the heat of the reaction. Okay, Q is what? The heat of reaction, because the reaction is occurring at constant pressure. So your heat is equal to the enthalpy change. So you have seen these things in thermodynamics. Now, next, let us go into detail of this all. Okay, so how we can do this? So the above reaction we have seen can be done in multiple steps. First is the conversion of the M solid, that is the metal solid, into gaseous, and this is called as sublimation. So in this case, your energy, that is the enthalpy change, is equals to sublimation. Next is your change of gaseous metal into positive metal by release of electron, and this is called as ionization energy, or I. Second, the third thing is your dissociation of your say non-metal into what? Into its ionic, atomic form. This is called a dissociation energy. We have taken half because we are taking half of x2. Okay. Then we are adding electron to this x, so this electron affinity, and it is represented by minus e. Then we combine this x minus and this m plus that has been formed to give the mx solid. Now if you add all of these equations, you will get a final equation. Next is your lattice enthalpy and its calculation. So just we will continue that. So we can say that this delta H1, delta H2 that we got, sublimation, then your then your ionization, then your dissociation, and again ionization, and addition of these ions. All of this can be added to get the delta H of the reaction, or the heat of the reaction overall. So this can be alternatively written in this form: sublimation I, dissociation half, E and U. In case dissociation is not half, suppose you need two anions. So in that case, you will not have the dissociation. So this is just the case in case your metal is unimolecular. Means it requires one anion only. Okay. Or delta H can be written in this way also. So you bring this U here and you calculate a lattice energy, which is a required thing. Now, a number of ionic solids are almost insoluble in iron because the hydration energy is smaller than the lattice energy. So what does this mean? So whenever you want to dissolve an ion into water, you need some energy to break the lattice, and that lattice energy is being supplied by the hydration process. So whenever you dissolve the ion into water, it interacts with the water molecule. That attraction is attractive in nature, and attractive forces increases, therefore energy is released. Okay. As a result, that energy is used by the lattice to break the lattice into its ions. So example of so if in case your lattice energy is larger and is not enough that is supplied by the hydration, then we call that salt as water insoluble, like your AgCl, AgBr, AgI, Ag2CrO4, PbSO4, BaSO4, and COCO3. So these all are water insoluble. Now both lattice energy and hydration energy decreases with increase in ionic size. Okay, so this point is very important. So as you increase the ionic size, your hydration energy will also decrease and your lattice energy will also decrease. Now if both anion and cation are of comparable size, the cationic radius will influence the lattice energy. Okay, so if your ion are not of comparable size, then increase in ionic size decrease the lattice energy. But if they are of comparable size, then the cation radius will influence the lattice energy. Okay. Now covalent bond are of two types. First is the non-polar covalent bond. So in case of similar element combining, so H2Cl2, same element is combining. So since there is symmetrical distribution of electrons, so they are non-polar in nature. Whereas in case of polar covalent bond, your molecule, the atoms that are combining, that are having different electronegativity and different distribution of electron. So they are polar. So this is polar, this is polar. Both are polar in nature. Now the greater the difference in electronegativity, higher is the polar nature. It is very obvious because electron density will be, you can say, will be polarized much more. Okay, it will be attracted towards the more electronegative one if there is a higher difference in the electronegativity, and the relative order of electronegativity of some element is, so the fluorine is the most electric, then is the oxygen, then chlorine and nitrogen are almost equal, bromine, then sulfur, carbon and iodine are almost equal, and then is the least electronegative, which is hydrogen. So these are the electronegativities of the non-metals. Next is the calculation of percentage ionic character. So how we can calculate it? There are several methods. First method is Pauli's equation. So in this we use the electronegativity of A, we subtract, take the difference where chi A is greater than chi B, multiplied by 18 and take the power 1.4 for the difference of the electronegativity. Or the Hanna-Smith equation, which is this, which is 16 chi A minus chi B plus 33.5 chi A minus chi B square. Very simple, all things you know. So this is the electronegativity difference. So chi A is greater than chi B again. Remember this. Next is dipole moment. How we can calculate it? So you know the dipole moment can be calculated using charge and distance. So its formula is Q cross D. This is a cross product of charge and distance, and in CGS system, its unit is dBi. Now our dipole, our molecule is said to be polar if the net dipole moment of the molecule is not zero. Like in the case of NH3 has a low dipole moment than NH3 because the resulting vector is towards the lone pair in NH3, but in NF3 it is opposite of lone pair because of the high electronegativity of fluorine. It is towards the lone pair, towards the fluorine atom. But in case of hydrogen, hydrogen is very less electronegative, so most of the electron density is towards the lone pair and the dipole moment distance is toward that. So remember this, that the direction of dipole moment goes from positive to negative. So you will see this in chemistry, but in physics this thing is opposite. Remember this thing, this may confuse you. Okay, so talking more about dipole moment, if you compare these two, so this is the image that you will get. Okay, so this is your NH3, your N and lone pair will go here, and this all will go upside, so that will result upside. But in this case, this is opposite of this. This true is for lone pair it is going upside, and for fluorine it is going downside. And since there are 3 fluorines, this will out raise this thing, and net dipole will go down. So if you calculate the dipole moment, it is 4.90 into 10 to the power minus 30 for NH3. Therefore, NF3 it is less because they are opposing each other, whereas these are adding to each other and getting their net towards upside. Now, percentage ionic character can be calculated using this formula. It is very, very important. Question is often asked from here. So it is mu observed by mu ionic. Means you will see that mu observed, mu ionic. So observed is what? It is the experimental one, and ionic is the calculated one. It is totally based upon the thing that your compound is ionic. In that case, it is calculated. Okay, multiplied by 100. Now this ionic is calculated by Q multiplied by D, where Q is 4.2 into 10 to the power minus 10 ESU. So this is your CGS unit. So we are taking it as the charge on one electron because we are assuming that the compound is completely ionic and the electron is getting completely transferred to one of the element. Right? Okay. So the charge becomes equal to the charge of electron. What is partial ionic character of covalent bond? So on the basis of electronegativity difference, partial ionic character of covalent bond can be summarized. So there is short summary of that. So if your electronegativity difference between 2 is 1.7, then the partial ionic character is 50% ionic and 50% covalent. If that difference is greater than 1.7, then it is your ionic character is more than 50%. If it is less than 1.7, then the ionic character is less than 50%. Okay, very obvious. Difference will increase, electronegativity difference will increase, ionic character will increase, electronegative difference will decrease, ionic character will decrease, and covalent character will increase. Okay. Now, but if it is equals to 1.7, then both are 50-50%. After next thing is Fajan's rule. So, according to Fajan's rule, it is said that our covalent character is dependent upon the size of the cation and anion. So, if there is high polarizing power, then the molecule will be more covalent character. Let us try to understand this high polarizing power. So this high polarizing power is generally associated with the size of cation. So if your cation is small in size, that means your charge density is very high because the same charge is distributed over a small area. Now higher charge density means greater force that will help to polarize a given molecule more. So what is the molecule that is getting polarized? It is the anion. Okay, the anion, when its size will increase, means the charge is distributed all over the larger space, and that negative charge is being under small small area of influence of the nucleus. So there, that negative charge is being dispersed over a large area. So if that is dispersed over a large area, it can be easily attracted by the cation. Okay, so you get this thing. So one charge is getting distributed and one charge is being contracting. So that contracting charge will have a effect on that dispersed charge, and that will try to polarize that anion, and due to polarization, negative your electron density is towards the cation, and that results in an overlap. And whenever an overlap occurs, you will see a covalent bond. So charge on anion is also directly proportional. So if the charge on anion is increasing, on ions increasing, then what you will see that your covalent character will increase according to Fajan's rule. So in between NaI, NaCl and NaI, NaI is having a larger size of the anion, which is I minus. So it can be easily polarized. Therefore, it has a more covalent character. Okay. Similarly, if you consider the case of FeCl2 and FeCl3, now this Fe has a greater charge, so that results in a greater polarizing power of the of your ferric ion, and hence it will polarize your chlorine more. So again, the covalent character is increasing in case of FeCl3. So cation with pseudo noble gas configuration has a higher polarizing power than the other noble gas configuration cation. Okay, so this is also a very important point. Next is a formal charge. So what is formal charge? So it is the difference between the number of valence electron of that atom in an isolated or free state and the number of assigned in the Lewis structure. So it is basically the number of electrons that has been assigned extra during the formation of Lewis structure. So it is basically the number of valence electron in the free atom first of all. Now we'll subtract what? We'll subtract the number of non-bonding electron, and we will subtract the number of bonding electron. So we will do this. We'll do the half and subtract it, because one is being on the one is being on the other atom. So we'll take a half of it. So in this way you can easily calculate the formal charge, that what is the charge that has been developed. Clear? Okay. Next are the bond parameters. So there are bond parameters which help us to define the whole molecule. So these are bond length. So it is basically the distance between the nuclei of the two atoms, and it depends upon the size, atom, hybridization, steric effect, resonance, etc. So it depends upon all of this. Okay, and the bond length increases, the size of the atom or orbital also increases, because orbital size increasing, then the bond length is increasing, and also the stability of bond decreases because they are inversely proportional. Next is bond enthalpy. So it is the amount of energy that is required to break 1 mole of bond between two gaseous atoms. Now bond enthalpy is directly proportional to electronegativity. More is the electronegativity difference, more is the bond enthalpy. And inversely proportional to size of the atom, because size of the atom will increase, bond length will increase, therefore bond enthalpy will also decrease. Why it will decrease? Because now the electrons that are being present in this bond are under a less influence of the nucleus, because they are far from the nucleus because of the longer bond length. As a result, they can be easily broken, when the bond can be easily broken. And the number of lone pair is almost also inversely proportional. So if there are more lone pair of electron, the bond enthalpy is also less. Next bond parameter is bond order. So it is simply the number of bond between two molecules, between two atoms in a molecule, and more is the number of bond, shorter is the bond. Okay, means the bond order is inversely proportional to bond length, we can say that. And bond stability is directly proportional, because the bond gets shorter, bond enthalpy increases and it becomes more stable. So more and more bonds are there to attach to two atoms, the bond stability increases. Okay, next is, if you come to calculate bond order, is simply number of double bond by number of delocalized position. Suppose for O3 we know that there is one double bond, and there is 1 plus number of double bond is 1, and the number of delocalized position is 2. So 3 means there are 2 extra oxygens. So 2 positions are there. So it can be between, suppose I am numbering O1, O2 and O3. So this double bond can be between O1 and O2, and can be between O2 and A3. So there are 2 delocalized positions, so we are writing it 2. So that will result in 1.5. Similarly, SO4 2 minus 2 double bonds are there, and 4 positions are there. So between since there are 4 bonds between S and O, so 4 delocalized positions are there. That will result in total of 1.5 bond order. Next is your bond angle. So it is defined as the angle between the orbitals containing bonding electron pair around the central atom in a molecule or a complex ion. So this is a bond angle, very easy to understand. So you can see that this is your bond pair and this is the bond pair. The angle between these two is what? Your bond angle. Next concept is resonance. So resonance is seen in molecules like CO3 and O3, CO3 2 minus and O3, in benzene, ozone, nitric acid, and many more. So it is used when one single structure cannot explain the whole compound. So in that case, you require multiple structure to explain that. Okay, and your actual structure is actually the intermediate in bit of all this structure. So for example, this is ozone, and this is also the structure of ozone. Now this double bond can be here and here also. So it is being seen that it is partially present on both sides. Okay, so as a result, we can say that your these are the two resonance structure, and this is the intermediate that has been presumed. Now this is called resonance hybrid, and this is not the actual structure, but it is a hypothetical structure that we consider. Now you can see here that this is the double bond that we have. So I'm talking about the formal charge. So it is one how it's, sorry, not the formal charge. I'm talking about the bond order. So you can see that there is one double bond and there are two positions, this one and this one. So that is the reason I was taking the number of double bond as 1 and the position as 2. That will give you 1.5 bond order. So this is having 1.5 bond order here and 1.5 bond order here. Means this electron that is present is been delocalized in two positions. So half and half. Now resonance is shown only by those molecules which possess conjugate single and multiple bonds, and it imparts stability. So more and more number of resonating structure, more is the stability. And since the electrons are not localized between any particular atoms and are uniformly distributed in the resonance hybrid, all the bonds are similar. Like this and this bonds are almost similar and are of equal bond length. Now resonance average the bond characteristics as a whole. So what are we doing? We're averaging it. We're averaging both of this, and we're saying that the actual structure is average of both of this. Next is the difference between the resonance hybrid and the most stable structure is called the resonance energy. Because suppose now these two are the equivalent resonance structure. Now suppose two resonance structures are there. Out of that, one was more stable. Now we will take the energy of that, and we will take the energy of our resonance hybrid. So your resonance hybrid energy minus the resonance energy minus the energy of the most stable structure gives the resonance energy. So that is the energy, extra energy stability that has been provided by the intermediate structure, and it is being formed by the averaging of all the resonance structure. Next is coordinate bond. So coordinate bond is formed. How it is formed? It is formed by the complete donation of one of electron from one atom to another. So one atom is the one which is donating electron, and the other one is the only receiving one. So that result in the formation of coordinate bond or dative bonding. So suppose this is your example. Here your lone pair is being donated completely to H. Okay, so this is, there is a bond between N and H, but the electrons between the bond are of nitrogen only. So this bond is called as the coordinate bond. Okay, so that results in this NH4 plus. Similarly, this is called as the coordinate bond because your N is donating your electron to the B, and boron doesn't have an electron in this bond. Now the chemical bond that are formed by the sharing of electron between the elements of the same electronegativity or between the elements of having less difference in electronegativity are called covalent bond. For example, O2 molecule. So this is the example of covalent bond. Next is Valence Bond Theory. So this was given by Pauling and Mulliken. So it explains the formation of orbitals in terms of overlapping. For example, if H2 is formed, so it is formed by the overlapping of atomic orbital of two hydrogens. Okay. So in this case, 1s orbital of one hydrogen overlap with the 1s orbital of other hydrogen to form the H2 molecule. So because of orbital overlap, the electron density between the nuclei increases, because this is the region where the overlap is taking and the influence of two nucleuses is more. So the oppositely charged electron tends to occupy that area. Now the overlap of this orbital may result in two types of bond. So first is sigma bond. The sigma bond is formed by the head-on-head overlap. So this can be explained using this diagram. So this is what? S and S orbital are overlapping head-on-head to form the sigma bond. So this is called SS overlapping. Then overlapping axially. Again, S and P orbital can overlap head-on-head to form the. So this is the area of overlap, and this is SP overlapping head-on-head. So this is called sigma bond because they are overlapping head-on-head. Next is the pi bond. So how it is formed? It is formed by the incomplete overlap or side overlap, as seen in case of p orbital. You can see here these are the two p orbitals. They are overlapping side by side, and this is the small area of what overlapping. Now this is not head on head. If they have been overlapped through the using this area, then that case we will call it as head on head overlap. But they are using the side on, because this is a side, this is another side. They are overlapping with each other to form the pi bond. Now if you consider a double bond, then generally, I'm saying it generally, there are exceptions to it, that you will generally see that out of these two bonds, one is sigma and another is pi. If you are seeing a triple bond, then you will see that Two are sigma and one is pi. One more thing that is important is that pi bonds are weaker than the sigma bond. Now, concept of hybridization involving s, p and d orbital. So this was given by Pauling. He said that the atomic orbital first intermix and then they form orbitals which are called hybridized orbital, and those hybridized orbital have the same shape, same energy and same size. So this is very important, right? And thus intermixing is always between the atomic orbital of comparable energy. So these two things are important. First, the shape, size and energy of the resulting orbital is same. Hybridized orbital is same. So this is often misunderstood by the student. They don't get this point correctly. Okay, the size and shape and size all are same, and the number of atomic orbital that are combining is equal to the number of hybridized orbitals that is formed. So this is also an important point. Now next is an example. So suppose sp, sp2, sp3 hybridization of atomic orbital of Be, boron, carbon, nitrogen and oxygen are used to explain the formation of geometric shape like BeCl2. So BeCl2 is linear and it is formed by sp hybridization. BCl3 it is sp2, CH4 sp3 and NH3 also sp3 and NH2 also sp3. So they can be explained using this hybridization concept. So one more important thing. So we are just doing it in short. So what we will see that if we take the dsp2 configure dsp2 hybridization, then the d orbital that is involved is dx square minus y square, and this is dsp2 is corresponding to square planar shape. Whereas if we take sp3d, which is your trigonal bipyramidal, then in that case your d orbital that is involved is what? It is your dz square. And if it is sp3d2, then the 2d orbitals that are involved are dz square and dx square minus y square. Clear? Okay. Now moving on to next. If you are taking dsp3, then your dz square is used, and if the shape is trigonal bipyramidal. Okay, clear? So this is trigonal, and if it is dsp3, then what is the orbital that is being used? Then it is dx square minus y square, and this is square pyramidal. So this is the difference. Okay, so in this case sp3d is used for trigonal bipyramidal, and in case of your square pyramidal dsp3 is used. Clear? And the d orbital that is involved in case of triangular bipyramidal is dz square, and in case of square pyramidal it is dx square minus y square. If you consider the case of third period, then 3d orbital are comparable to the energy of 3p, 3s and 3p, as well as to the energy of 4s and 4p also. Now what is the result of that? That two types of hybridization are possible. First is 3s, 3p and 3d. Second is 3d, 4s and 4p. So you can see these two types of configuration. Sorry, these two type of hybridization or mixing. That your 3s and 3p and 3d will combine. Also your 3d, 4s and 4p can also combine. Next is some examples are there. So if you take square planar, it is dsp2, and the dsp2 example are NiCN4 whole 2 minus PtCl4 2 minus. If you are triangular bipyramidal taking, then sp3d hybridization is possible, and it requires 1s, 3p and 1d, that is pf5 and pcl5. If you are taking square pyramidal, then sp3d2 is the one, and your molecules are BRF5 and IF5, and octahedral can take sp3d2 and d2sp3 both hybridization, and that would result in SF6 CONH3 whole 6 3 plus and CRF6 whole 3 minus. Next, some important examples are, so sp3d hybridization example is PCl5. So you will see that in PCl5 the axial bonds are longer, whereas the equatorial bonds are shorter. Now since the axial bonds are longer, they are weaker than the equatorial bond. So therefore PCl5 is very reactive. So this is your equatorial bond that are present in the trigonal planar, and this is your axial bond that is present along the axial position. Okay. Next is your sp3d2 hybridization. So if you see the SF6, you will see that the every SF bond is same, and as a result of same bond length, they formed a perfect octahedral, and it is symmetrical in nature. Due to this reason, they are very less reactive. So this is your overall shape. This is octahedral, and each bond are having the same length. Next is, there is a formula to know this x, or to know the shape, which is given by x is equals to half v number of valence electron, m is what? Number of monovalent atom, a is the charge if it is anion, and c is the charge if it is a cation. So it is written here also. So this is M, number of monovalent, anion and cation. Now, if you want to determine the hybridization of atom, pi bonds are not considered. This is very, very important that you see there are 5 bonds. Then if it can be sp3d or dsp3, that thing is good. But all those 5 bonds should be sigma and not pi. This should be kept in mind. But lone pair are always considered. Okay. So next is VSEPR theory. So this was given by Gipsy and Neron. Its full form is valence shell electron pair repulsion. So in this case, what happens? Bond pair arrange themselves so that the repulsion can be minimum. Now that results in two types of electron pair. First is bond pair and the lone pair, and the repulsion can be of multiple types. So this is the order of repulsion. So there is a maximum repulsion between lone pair and lone pair because they are not under the influence of two nucleus but one nucleus only. So there is maximum repulsion. Then is lone pair and bond pair, and minimum repulsion between bond pair and bond pair. Now hybrid orbital and molecular orbital involved, sp and d orbital are this. Okay, so if there are two bond pair, the shape is linear. Now the most important thing about shape is that we don't consider the lone pair. So two bond pair linear, three bond pair trigonal planar. Okay, two bond pair and one lone pair bent. So these two have the same hybridization, whereas these three have the same hybridization, these three have the same hybridization, and these three have the same hybridization, and this is the individual hybridization. Now if you see the same hybridization having different shapes depending upon the number of lone pairs that are involved. 0 lone pair tetrahedral, 1 lone pair pyramidal, 2 lone pair angular or V shape. Similarly, no lone pair triangular bipyramidal, 1 lone pair seesaw, 2 lone pair T-shaped. And if you consider the geometry, then geometry will be same. That means if your hybridization is same, then these three will have the same geometry and all have the tetrahedral geometry. Similarly, these three will have the triangular bipyramidal geometry. Okay, and these three will have the octahedral geometry, but their shape will be different. Like your octahedral, if it is 0 lone pair, it will be octahedral. Sorry, it's 6 bond pair, then octahedral. 1 lone pair square pyramidal, and 2 lone pair square planar. Last is the IF7 example, which is pentagonal bipyramidal and having a hybridization of sp3d3. Now, the most important theories are we have seen Valence Bond Theory, and then we have seen the hybridization concept. And then now we are moving to the VSEPR theory. VSEPR theory has also completed, sorry. And now we are moving to the molecular orbital theory. This is the most successful theory of all. So what we do is that we are not assigning the electron to one atom. Instead, what we are saying that it is distributed or under the influence of two nuclei, right? And it is formed by the combination of atomic orbital, and the second most important thing is that they will also consider the inner valence orbitals. So inner orbitals. So they will not consider the valence orbital only, they will consider the inner one also. Because this is the main difference. Because in each of this that we have seen, we are considering the outer or valence shell. But in the molecular orbital theory, the inner shells are also considered, and that is the reason for the successful quality of this MOT. It was given by Hund and Molliker. So molecular orbital are two types. So first is so if two atomic orbital combine, then they can result in two type of molecular orbital. So one will be of Colby bonding. They can be sigma or pi depending upon their combining way, and it can be anti-bonding if it is higher in energy. So if two atoms are combining, atomic orbital are combining, then one will be raised in energy and one will lowered in energy, keeping the overall energy constant. So this follows the conservation of energy also. Clear? Now the bonding will be shown by sigma and the anti-bonding will be shown by sigma star and pi star. Now if your electron is entering the sigma or pi, which is your bonding one, then that will result in more stability. If it is going to the anti-bonding, then it will result in less stability. So if you write the electronic configuration for molecular orbital, it is written in the same way. So for species like O2 and F2, it is given by sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, sigma 2pz, pi 2px, 2py, pi star 2px, 2py, sigma star 2pz. But for species like lithium 2, beryllium 2, boron 2, carbon 2, nitrogen 2, it is given by sigma 1s, sigma 1s star, sigma 2s, sigma 2s star, pi 2px, pi 2py, sigma 2pz, pi star 2px, 2py, and sigma star 2pz. So this is the difference. Here the difference lies in both of this. All other are same. Okay, so when you go after nitrogen, then you will see from oxygen that the order is been reversed, and this is the order that would be accepted. Okay, because this is raised in energy, then this is higher in energy by the same amount. Similar goes for this, but due to a very strange phenomena which is called as sp mixing, we see this type of configuration for the lower atoms, because the difference in energy between s and p orbital is less, and s and p orbital, they do overlap before overlapping with the other atomic orbital, and that results in a raise in energy for sigma 2pz. Okay, now if you want to calculate the bond order, it is given by number of bonding orbital bonding electron by number of anti-bonding electron divided by 2. So same thing is mentioned. Now if your NB is greater, that is bonding orbital is greater, then the bond order is positive and your molecule is stable. If your anti-bonding is greater, then in that case, or your anti-bonding is same, then in that case also your bond order will be negative or 0. So this thing is not possible, because we always start feeling from the bonding one, then we go to the anti-bonding for each corresponding thing. So this case is only possible. Okay. Now magnetic behavior of a molecule can also be explained. This is the most important thing. So if you see that upon the filling of a molecular orbital, you see a unpaired electron, then that will be paramagnetic. If you don't see one, then it is a dimagnetic. The formula is n into n plus 2 root under Bohr magnetron, where n is the number of unpaired electrons. Okay. Next is hydrogen bonding. So whenever you see that your hydrogen is attached to fluorine, oxygen and nitrogen, in that case only, okay, remember this, if your hydrogen is attached to these three atoms, then and then only your hydrogen is capable of hydrogen bonding. Although your Cl is much more electronegative, it is not possible. So basically what happens is that whenever hydrogen is attached to these three atoms, it interacts, or it has a positive charge, delta positive charge. Now the delta positive charge interacts with the lone pair of other electronegative element, and that is called as hydrogen bonding. So for example, we see it in HF. So you can see that two type of hydrogen bonding are possible. First is intermolecular, which is between the two atoms, which is two different molecules. Okay, those two atoms are of two different molecules. Example, between these HFs, right? So you can see that this negative part of HF, that is fluorine, interact with the positive part of the another HF, which is hydrogen. So this thing increases the decreases the volatility and increases the boiling point, because now molecules are held tighter to the hydrogen bonding, that is decreasing the volatility and increasing the boiling point. Now viscosity is also increased, because now there is a much more adhesive forces, and surface tension is also increased, because the net force that was not balanced is the surface tension, and the net force has increased due to the what? Due to the hydrogen bonding. Clear? Now next thing is intramolecular hydrogen bonding. So this increases the volatility, because that disrupts the interaction with the other molecule, right? And hence it decreases the boiling point, and also decreases solubility, because the negative part that was being available for interaction with the water is now being captured by the atom that is within the molecule. Okay, so this is the example that a hydrogen that was that should be available for the other molecule to combine, or the water molecule to combine. Both of the cases are disrupted by this hydrogen bonding, and hence your boiling point is decreased, and solubility is also decreased. So due to this hydrogen bonding, H2O is extensively having a higher boiling point than HF, because the number of hydrogen that are available for hydrogen bonding is more. Although HF is having a electronegative F, but still due to the greater number of hydrogen available for hydrogen bonding, that is having a greater boiling point. Now hydrogen bonding is strongest when the bonded structure is stabilized through resonance. So this is also very important. Now various type of effect due to hydrogen bonding are as follows. So first is the polar nature of H2O. So H2O is very polar in nature, and it has an abnormally high boiling point, although it is having a very low dipole moment and a low molecular mass. So this is the reason that one H2O is being combined to 1, 2, 3, 4, 5. Total of how much? 5 water molecule. Okay, so that results in a pentacoordinated system. sorry, are joined to 4 atoms. Sorry for that. So one is attached to 1, 2, 3, 4 atoms. So it is having a four atom quadrant. Okay. So next thing, the coordination number is 4. It is mentioned here also. Next effect is that we'll see that whenever an ice is formed, its volume is increasing, because when the volume, say temperature is lowered, the molecule comes closer and closer. Okay, so up till 4 degrees Celsius they will come closer, but below that they just move apart and the hydrogen bonding between the ice is broken, and that results in an expansion of the volume. Now the same mass is being expanded over greater volume and the density is decreased as a result of that. Okay, so 4 degree Celsius is the temperature at which you will have the highest density, right? At 1 atm pressure, I'm telling it. Now in the gaseous form, HF molecule is also seen to form a very beautiful penta-coordinated system. So it has yeah, 1, 2, 3, 4 and 5. Okay, this will be not there. So penta-coordinate system, you can see how beautifully this shape is formed in case of vapor phase, and the distance between two H and F, which are say hydrogen bonded, is 150 picometer, whereas the covalent bonded is having a distance of 101 picometer. You can see how close this bonding is, right? So from this you can evaluate that extent of or the strength of hydrogen bonding. Now carboxylic acid also dimerizes. See, and due to this dimerization, the H plus availability is also decreased. So the acidity of this say compounds are also affected by the hydrogen bonding, because now it is attached to two oxygen atoms, one by covalent, another by what, hydrogen bonding. Next, the last topic is metallic bonding. So this thing, metallic bonding, is holding together the constituent particle in the metals. Okay, so this can be explained using two types of metallic bonding theory. First is the electron C model, in which it is believed that your electron that is present in a metal, they are dispersed over the whole crystal, and that delocalization has effect on the overlap. That has delocalization has the effect of what, compact closing of the lattice structure. Okay, and this creates a sea of a mobile electron, which results in the conduction property of the metal. Another is that your atomic orbital of two metal, they overlap and form two types of band, which is conduction band and valence band. Now when the electron go from conduction valence band to conduction band, it helps to conduct electricity, and more number of electrons in the conduction band means more electricity or more good conductor it is. So if your energy gap is very high, then it is an insulator, because now less electron can go to the conduction band, and this is energy gap, means that the energy difference between the conduction band and the valence band, as simple as that. Now if you increase the temperature, your electron will get enough energy, so it can go from a conduction band to the valence band, and hence it will increase the conductivity of that given metal. Now if I try to summarize all of this, first point is that the atomic orbital, they combine to form the new hybrid orbital, which are having the same energy, same size and same shape, and this phenomena is called hybridization. And the dipole moment is what? It is the measure of the polarity of the bond calculated by Q multiplied by R, where Q is the charge and R is the distance between that charge. Now Fajan's rule helps to predict the degree of covalent character. More is the size of anion and lesser is the size of cation. It will result in more overlap and hence more covalent character. Okay. Lattice enthalpy is the energy released when gaseous ion forms an ionic solid. So whenever you take, suppose you take Na plus gaseous, Cl minus gaseous, you combine each of this, then some energy is released due to the positive or attractive interaction, and that is called the what? That is called your lattice enthalpy. That heat release is called as lattice enthalpy. Now in a resonance, molecule can be represented by two or more valid Lewis structure. Okay, so that thing is called as resonance, and each of the structure is called resulting structure, whereas the average of each of these is taken in terms of resonance hybrid, which is a hypothetical structure that we keep it for our reference. Okay, so this was for today's session. Thank you.